Alright folks, this section is the work energy theorem. Here we tie everything together now, and it's going to bring in material from the first chapter, second chapter, and this one. So it's a big tie-in. So we'll look at connection between work, velocity, acceleration, force, energy. Now, what you need to learn from here is that any work done, if there isn't friction involved, is changed to energy of motion. So we look here at the young fellow pushing the boxes here, trying to skate. The ice is a frictionless surface, so any of the work that the person does gets converted directly to energy of motion. And in the blue box here below is a little summary. Work when done on a perfectly frictionless horizontal surface is transformed into kinetic energy. So work done is equal to the change in kinetic energy of the object. Okay, so what does that look like? So in example 1 here, Keith uses a force of 230 newtons to push a box that has a mass of 75 kilograms from rest across a smooth frictionless gym floor. So what's the acceleration of the box? Well, the overall force, or force net, is equal to the force that's applied, which is 230 newtons. So your force net is what's the overall forces going on here. And there's only one force involved since there isn't friction, and that's the applied force of 230 newtons. So to calculate your force net, it's mass times acceleration, and we're asked to find the acceleration. So divide both sides by mass, so you have force divided by mass, and you would end up with 3.07 meters per second squared. So then what's the velocity of the box after 55 meters? Well, if you look at your given information, you have a distance. You know the box starts from rest, so V1 is 0. You're asked to find V2, and you have acceleration. So if you look through kinetic formulas, you're asked to find V2, so you have acceleration, you have distance, you know V1 is 0. So put in the values that you know. So you're going to multiply this side. V2 subtract 0 squared, this is going to be 0. So that's not going to do anything for you, it's going to disappear. So your formula will become V2 squared equals whatever this value is. And if you do the calculations, it's 337.7. To get rid of the square, you take the square root, and you have 18 meters per second. So let's come up with a formula now for the work energy theorem. So we'd said in the first slide that work is equal to change in kinetic energy. Now that's assuming it's frictionless and a smooth horizontal surface. So you change in kinetic energy. So that would be your kinetic energy, that would be your kinetic energy at the beginning, subtract kinetic energy at the end. Kinetic energy at the end, subtract energy at the beginning. The formula for kinetic energy we already covered is a half mv squared. And work is also calculated by force times distance. So in this formula, if you had force, distance, mass, and velocity. Alright, so try using that formula in this example. How much work is done by a triathlete who accelerates herself on her bicycle, and there's a combined mass of 105 kilograms, and the cyclist is going to go from 5 meters per second to 10 meters per second. So how much work is done? So take a moment and do that. So I'm going to assume that you've just unpaused the video. And we know that work is equal to change in energy. And that would be your change in kinetic energy. So kinetic energy at the end, subtract kinetic energy at the beginning. So rewrite the formula using the variables. And then fill in the values you know. So from here, and this is at the end of the motion, mass stayed the same, the person didn't lose any mass. So mass is still 105. Velocity at the end was 10 meters per second, and velocity at the beginning was 5. So square 10, multiply to 105, and multiply by half. And you're going to subtract that from the value here, 25 times 105, subtract a half. So work at both these sides, and you should have come back with 3,940 joules. Now another example. So again, pause and give it a try. Alright, so assume that you've had time to look at it. So an 80 kilogram sled is initially at rest on a frictionless horizontal ice surface. A force of 220 newtons acts on the sled over a distance of 5.2 meters. Calculate the final speed. So you have a sled that's at rest, so you know your V1 is 0. You're going to apply a force to the sled, and you're going to get the sled to move. So if this is your sled, and your sled's going to move, and you apply your force of 220. Now there isn't any friction, so the only force involved is the applied force, because you were told it's a frictionless surface, so you don't have anything pulling you back, so you don't consider friction. And you're given the distance that sled moves. So again, work is your change in kinetic energy. Now, you were given the force, a distance, and now you're changing kinetic energy. So substitute in the values. No, the change from this question to the last one is that we substitute in the values for work. The work can be found using force times distance. So you go through this question. It's your 220 newtons applied force times the distance you travel. So that's the work that will be done. You fill in each of the values you know here. And again, we said V1 was 0. The mass of the sled hadn't changed, so still 80 on both sides. But you have to find V2. So you work at this side, your left side. You come back with 28.6. And then you're going to have a half times 80, and this side over here is going to be 80 times 0, so this is not going to play any part in your question because it's going to cancel itself out. So on this side you're going to have 40v squared, and you're going to divide that into your answer from here and come back with 28.6. So again, try these calculations. When you get down to v squared equals, you should have had 28.6. Then your final velocity is 5.35. because you need to remove the square root, or the square, by doing the square root. Alright, so car is stalled and stopped. To get it started again, two people push the 1,300 kilogram vehicle with a combined force of 800 newtons, and they push the car for 1.6 meters, and the surface is again horizontal and frictionless. So what's the final speed of the car when the driver pops the clutch to restart the car? So again, the car is stopped. So here's your car. You're going to push it, and it's going to get pushed 1.6 meters before it starts again. You know the mass of the vehicle. You know that the velocity at the beginning, because it stopped, is 0. And you're asked to find V2. And the amount of force to get the car to move, the applied force, was 800 newtons. So work is your change in kinetic energy. Work is force times distance. So if I just look down here on the left side of the equation, you fill in your force times distance, 800 newtons times 1.6. So then you find out that 1,280 joules were used to move the car. Now let's concentrate going down through here. So this we've already been over. Now you fill in your values: kinetic energy at the end, subtract energy at the beginning, mass of the car, and again the same on both sides. But where the beginning velocity was 0, and you multiply that through, it's going to cancel out this side here. So it's a half times 1300, 650. Your v squared is here. So to solve for v squared, you first have to divide both sides by 650. This is squared now. So to get rid of your square, remember to take the square root, and you get the final velocity to be 1.4. Okay, there's one last example. And it says an 8,000 kilogram aircraft is taxiing for takeoff, moving at 20 meters per second when the pilot notices there's only 100 meters of runway space left. He increases the engine's thrust. What minimum thrust, and that will be force here. So what minimum force will be required to allow the jet to reach its final takeoff speed of 70 meters per second? And again, the condition that has to be met for this example has to be a horizontal, frictionless surface, and we're not going to consider friction, which in this case for an aircraft would be air resistance. Now the change in this question from the last one is that your V1 is not 0. Your V1 is 20 meters per second. So work again. We've already been over this part, I'm not going to repeat it. So we're back here to our formula. We need to find force. So we don't know what that is. We do know the distance. The plane only has 100 meters of runway left. Its final velocity is 70 meters per second. The plane was at 20. The mass of the plane had not changed. So be careful when you're doing these calculations. Where mistakes usually happen is that sometimes people calculate everything through, then square. Remember to square here first, then multiply by 8,000, then a half. And the same here, 70 squared times 8,000 times a half. So when you do the left side, you should come back here with 18 million. Divide by 100, and you have 180,000. So here's the final force that's needed to get the plane to take off. So that's the end of this section. What I'll assign, not during Easter, but there'll be some practice questions when you return that I want you to go through, and I'll have this posted. And again, it's not a requirement that you do it during Easter, but I will give you some time to hand that in when we get back. So I'll have these notes posted, and they'll be there for class today.